I'm Ashley Jones, as I said, I work at Packet Clearinghouse, and this presentation is going to have a number of technical references, including, unfortunately, some configurations. So I'll try to keep it as high level as possible, but this is a very tactical talk on how to deploy the web server. So when we go through this, if you want to follow along, the slides are available, updated as of about 10 minutes ago at that address. Feel free to download the presentation. The configurations are followed verbatim, which I'll get into in a second to configure the server. So for this effectively demonstration, I assume that you have root, that you have an environment that supports Let's Encrypt. Let's Encrypt is a new CA that provides free certificates, and they automate the process so that you simply install their environment and away you go with the certificate automatic provision for you. So in this case, we're using Ubuntu, and Let's Encrypt also needs a publicly accessible entry in DNS so that it can get to your server to validate that you own that instance of the domain. So specifically for this talk, we'll be using Ubuntu 14.04. We'll be using Apache 2.4, and then the Let's Encrypt public beta. They're always updating their code, so be sure to stay up to date. So why encrypt? If you have a website that you're putting online, then it's accessible to people who would want to attack it. You should protect it always. If you think that you're safe inside your private network or behind your VPN, your firewall, there are internal hackers, and you should assume that they are going to be vicious players too. A little caveat there, Let's Encrypt doesn't quite work with internal addresses. For example, in the case of Firesheet, which is a browser plugin, I think America made reference to it. This plugin allows you on your browser to easily sniff full sessions for anyone else on the wireless network that you're on that's on an unencrypted wireless network, and trivially take over sessions to any website that you're logged into without you knowing, and it's all been clear and it's done in a programmatic way. We'll get to some of the weaponized examples in the next slide as well. And man-in-the-middle attacks, which is when you have clear traffic going across the wire, it's trivial to either listen to the traffic or more maliciously to alter the traffic so that you're not getting the same bits that you think you're getting. And with the SANOG revelations, we now know that even against state-level players, encryption works. If you're using the correct encryption, correct ciphers, then it's not really accessible for even a well-funded adversary to get at the traffic. So, as a little example, recently there was a scenario where a security researcher was in the Netherlands using a Vodafone 3G, 4G dongle to get online. And he was looking at a website, and he expected it to look something like this. And in fact, when he looked at the source code for his website, what he saw was that there was, the traffic had changed, and he didn't know why. And it was obfuscated. The address of this JavaScript is cited as 1234. I'm not sure if that's a literal IP address or just the example. But the point is that it was unknown what was happening, and it's because his connections were happening in the clear that the man-in-the-middle attack was able to happen. And this is not happening in a regime where they're trying to oppress their citizens. This is happening in the West, where it's supposed to be safe, and it's happening with a provider that's supposed to not be doing things. In the end, what was happening was that Vodafone wanted to change the traffic to reduce image size to supposedly have a better performance for the end user, but because they weren't doing it explicitly without your permission, it looked very fishy, and there was no way to opt out, I believe. So this is just an example that you should encrypt because you want your traffic to stay your traffic the way you want it to be. So you can set up encryption, and as again speaking to America's keynote, you could accept the defaults, but you shouldn't. You should encrypt well. And the reason is that there's always more and more attacks. Sorry, we skipped the IPv6. So if you configure your web server, and we'll get to that in a second, for IPv4, there is zero effort to configure it for IPv6. You get the same configurations that work for IPv4 using SNI, just work with IPv6, and this is great. So assuming that your provider has IPv6 for you, You need to encrypt well so that you're protected against the latest threats and vulnerabilities. There's all these catchy buzzwords, and every time they come out, you need to update your configuration and your server software to make sure that you're up to date, and that means you need to encrypt well. When something like Heartbleed comes along, it's not much longer until it's weaponized. And when it's weaponized, it means that anyone can download a script, point it to a web server, and get private certificates, get passwords that are in memory, and the script kiddies or the hackers who just want to download something and double click to get what they want, it's trivial. So that means you need to stay up to date and encrypt well. And another reason is that HSTS, which is HTTP strict transport security, this allows you to ensure that after the initial visit to port 80, traffic is always redirected to port 443 without that initial request to port 80. And this does two things for you. The first thing that it does is it reduces that overall chatter on the wire and reduces the number of handshakes to get the client to their data. And it also means that subsequent traffic to your server will only be sent over 443. The browser will cache the connection that it has HSTS support in the server, and no traffic will be sent unencrypted, which is a huge win for security. And then finally, it's not hard, and that's what I'm hoping to show you here today. There's a number of tools that will make this easy for you. The configurations that I'm showing today, they're taken from Cypherlist, and there's the URL for here to take reference. And as well, if you are running Nginx, or if you're running Lighty, or any other web servers out there, there's great configuration tools. Mozilla's TLS configuration generator does a great job of walking through the specific versions you have, OpenSSL, which versions of Apache, and they'll custom tailor the config that pops out, and you can drop that right into your server. It's great. And then finally, after you have your configuration done and deployed, you can test it to ensure that's as good as you think it is with Qualys SSL Labs. Has a great SSL tester on their site. We'll get to that as well. So now, as I mentioned, what I'm going to show here is a verbatim install. I took a clean image on Linode and provisioned Ubuntu 14.04, and I logged in as root and I ran these commands. And at the end, you'll end up with a secure instance. So this first line is actually not anything to do with Apache, but just a good reminder, you need to stay up to date and you need to keep upgrading. So for Ubuntu, this is apt-get upgrade and apt-get update. The next three lines, we install Apache, as well as Git, which we need for the Let's Encrypt client. And then we enable certain modules for Apache, the SSL module, the headers module, and the rewrite module. And we enable the configuration of the security. These are normally all in one, but with the Ubuntu, the way they make the Apache 2 configs, you have to enable it. And here, this is probably a little too small. This is the kind of the meat of the matter when it comes to running the website securely. What we're doing here is we're specifying which ciphers we want to support, and these are ciphers that are known to not be vulnerable from any of the attacks. And then after that, we want to honor the cipher order so that we degrade in the most secure way possible from our more secure ciphers to the less ones. For the SSL protocols, all specifies that we want to specify all the ones that are out there supported, minus V2 and V3, which are vulnerable to downgrade attacks. SSL compression is also vulnerable, so we turn that off. And then we enable stapling and we enable staple caching. And what this says is that for the server, for the certificate revocation list, instead of doing an expensive round trip up to the CA to verify the certificate has not been revoked, we're going to cache that on the server, and we're going to preemptively send that down to the client if they ask for it. And again, this is a good security measure. One thing that I forgot to mention is that you'll notice these are configs that are being edited. So what we're doing is we are improving the default. You should not accept the default security. It's not going to get you where you want to go. We're going to add one file so we know at the top when we add it. The other thing that we're going to do in the default SSL config is we're actually going to use the snake oil certs that Ubuntu provisions for you. And what this does is ensures that you have self-signed certs that you can bootstrap later using Let's Encrypt into real certs. So we need to have enough of an environment to boot into TLS successfully for Apache without any errors. And then finally, in the security conf, we're just going to add two more lines. And what these two lines do is they prevent MIME attacks or cross-site scripting by enabling the no-sniff header. And as well, we prevent clickjacking, which allows you to prevent your site from being included in an iframe and then someone putting divs over that using fancy JavaScript and Z-index to jack to click, as they say. And then this is where we're going to create a new vhost entry. This is a simple vhost entry. If you are running an application, I presume, behind this, like any sort of PHP or Python or whatever application you have, you'll want to extend it to have your specifics. But in this case, this is just enough to bootstrap into a simple index page, which we'll see in a second here. So on port 80, all we do is, I'm looking at the white lines here highlighted, we redirect everything to port 443. Don't do anything but redirect. And then you notice the first line that's highlighted in the 443 vhost is where we set the HSTS header. And what this does is tells the client to never go back to port 80, and we set a timeout. There's a couple caveats to HSTS we'll get to on the next slide a little bit, you should be careful of. And again, we reference explicitly the snake oil certificates that are in this vhost, and the Let's Encrypt client will then overwrite those later, but we need those so that we can actually boot up into the vhost and be accessible on port 443, despite it having the snake oil certificates. Now we need to enable that vhost that we've created, and this is specific to Ubuntu, but all we're doing is restarting Apache after we put that vhost symlinked into the enabled sites. So we then reboot Apache, and we're ready to run Let's Encrypt. Some caveats. HSTS is totally awesome. You should absolutely run it. Except, if you include the include subdomain setting on this, you're in for a world of hurt. What will happen is you'll say for www, use HSTS, but include all subdomains. So that subdomain of dev.example.com that you use only internally suddenly will force you to use TLS on this dev instance that is only configured for port 80. On the API or any other subdomain that you have on your primary domain will be forced to use HSTS. Even worse, the client will viciously cache this. If you turn it off on your server, the client will still remember and will still try to go to port 443 on every subdomain for your primary domain. This is bad. That means you're talking to clients, you're talking to end users, you're talking to people who are not technical. You're forcing them to clear their browser cache, and it's hard to get out from under. So be very careful with this one. As well, some of the specific configurations that I mentioned are only applicable to certain versions of Apache. So be sure that you use the Mozilla TLS configuration generator before you go and deploy these. Apache will very kindly remind you that it can't boot when you have these in the wrong versions. Yeah, and then I mentioned again the Mozilla TLS configuration for finding out which of these specific configuration variables are applicable to your environment. All right, so now we have this new vhost set up. It's 1.tlstest.flip.com. You can go to it now. It's actually all configured for the end of this. So in this stage of the presentation, though, it only has a snake oil asserts, and you'll see that if you do the curl and you get just the headers, it's going to send a 302 header, tell you to go to HTTPS, and the HTTPS will return that it's invalid because you haven't told curl to ignore self-signed certs. We're doing good here. Now we need to install Let's Encrypt. Let's Encrypt beta right now for the auto provision client wants you to clone off of GitHub, and then you simply run the auto configure client, which and specify Apache explicitly. And now we're going to jump to some screenshots. So this is the ease of Let's Encrypt. We only have one vhost in this Apache instance. It's our test domain. You specify what your contact is for the domain, and you agree to their terms of service. And then it's going to prompt you to set HSTS headers because Let's Encrypt wants you to run secure. We've already set them, but you can go ahead and set them to be secure. Easy is if you want to have both port 80 and port 443 running concurrently. You get a nice good job dialog box, and you can go and look at that same vhost file that we just created and you'll note that it now has an extra line, and as well, your PEM and certificate is all set up for you. It's gone ahead and rebooted Apache, so if we run curl and use HTTPS, because we know the risk going to get redirected off of port 80, you'll get a grade 200. If you plug in the site into Qualys SSL Labs, you get an A+ rating. There are ways of getting slightly higher ratings. I was actually talking to a Mozilla developer, and he said that you can't quite get a perfect rating because you work in too many browsers. So A+ with the bars not quite maxed out is as good as you should expect when you're doing this. So let's go over some myths about TLS, because there's some hesitation to deploy it. The first one is that TLS is slow. This is a quote from Google about when they deployed SSL site-wide for all their search. And basically, we're talking very low single-digit percentage increase in overhead to support it. But more importantly, this quote came out in 2010. So in internet time, this is practically decades. This is a non-concern. As well, you can go to this great little site where I pulled this quote from. Is TLS fast yet? Hope you know the answer. Yes. There's another myth that Let's Encrypt requires root. In this case, it does, for the example that I gave, but there's actually a number of APIs and SDKs out there that allow you to do this in the old traditional way of generating a CSR, signing the CSR, signing into Let's Encrypt, or more firm ways again that only require root for a very, very small amount of this. Key management is hard, but in the case of refreshing your TLS certificates, it's actually very easy. As I mentioned, there's good command line tools, or in this case, there's this GUI, I guess maybe using quotes, for just reissuing the certificate either as much as you want within reason or just before it runs out. And then finally, this actually came up recently with a friend of mine just yesterday. He said, oh, how are you able to run so many domains on one IP? You need one IP address per TLS certificate. This is not true. Server name indication, SNI, gets rid of that. And before, you used to orphan some browsers when you did this, and it's no longer true. The problem before was that TLS handshake happened before you knew which domain you were requesting. So you had a chicken and egg problem. You get both the domain you're requesting as well as the TLS handshake happening at once. And as well, this is compatible with IPv4 and IPv6, which you can see again with this the test site that I'm referencing this talk. So let's go over some caveats about this, myths aside. As I mentioned, Let's Encrypt still requires a public IP. You can take the resulting certificates and put it on a private server, but when you need to renew the certificate, then you still require a public IP. Let's Encrypt is still in beta, and they're very clear about that. I encountered some very weird errors that I didn't understand. They were very easily resolvable with FAQs, and they have a great active IRC channel. If you're having any problems, I encourage you to head over there. They also have a very good forum, very current. Let's Encrypt does not support wildcard certificates. This can be a real pain if you have dozens or hundreds of subdomains. So be very cognizant of this before you jump ship to Let's Encrypt. They're also intentionally very short-lived certificates. Let's Encrypt wants them to be secure. Should your certificate and private key leave your control, you don't have too much worry, and you don't notice because you don't want to revoke it, then you only have 3 months before you need to renew it, and that other one will be invalid. And as I mentioned earlier, Let's Encrypt is only currently supported on a smaller amount of platforms. I initially went to run this demo on CentOS, which is what PCH uses for all of our production machines right now. And CentOS is not a supported environment, and thus nor is Red Hat Enterprise. When I ran this, it installed Python and a number of other supported platforms. So if you don't want to have that full suite of tools forced on your server, then you can use some of the other SDKs that are out there or get down to the raw API, which is publicly documented. And another warning, if you're running a site that you're used to very comfortably running port 80, you include whatever third-party JavaScript from maybe it's jQuery or it's a YouTube include to render a video, and you cut over to HTTPS, every asset that you include on your website needs to now be served from the HTTPS source. And this can be a problem because your end users in the browser will see, at worst, a little warning that maybe something isn't quite right, or sorry, at best a warning, and at worst, the page will fail.
All right. Keep on shouting. We're
All right. At worst, the page will fail to render, and your content won't be able to be seen at all. And you're also potentially orphaning some browsers. Now, SSL Labs, the qual site, will tell you specifically which ones you're orphaning. These are older versions of Android. They're IE6, thank God, and some other things. But you can be aware of this in case you have enterprise support or you have older browsers that you need to still be able to access your site. So that's it. Thank you very much. And does anyone have any questions? All right, Rick.
I'll just yell. So this is not something. Thank you very much. First of all, this is really. Does it work? Just quickly. First of all, thank you very much for this presentation. These are a lot of things that I'm sure many of us struggled with before they were automated, and just it was really useful to see that it's this easy now, and we don't have to spend weeks pulling equipment there. We have understand. We're trying to make these things work and getting these configurations to work. My question is a little bit more about the SSL certificate process, which is, I mean, there are lots of different stuff, which I know is not your specific thing. Is the root cert for Let's Encrypt in Microsoft browser certificates work? Will this work without anything popping up at this point?
This will work. It will work, yes.
That's
so
great. That's
the Let's Encrypt certificate CA has been signed by the root, and it's been shipped into the browsers so that they have the trust in there, which is awesome.
Hi. So one question really. So there's people that are talking about also not supporting TLS 1.0. And a lot of folks are saying that TLS 1.2 is the only thing that you should support, but of course people are worried about legacy devices. So what's your take on maybe even just like TLS 1.0 and just doing 1.1 or 1.2?
I think that you need to follow best practices and see what your environment is best suited for. So TLS 1.3, I believe, was ratified pretty recently, and that, the cipherless site that I pulled this from has the best practices for the most secure. If you think that you need to have browsers that need to support older versions, then you have to support them. But personally, I think we should go for the most secure possible so that we get the best security.
Right, thanks.
My question is about this process you demonstrated here is about getting integration browsers, right? So overall, I want to apply this Netflix script to my VPN client, Juniper client.
So you want to use the certificate and not the web server? Is that what you're asking?
Yeah, it's independent client. It's about TLS.
Okay.
Like Juniper client.
Yeah, so these are not endemic to Let's Encrypt. They're simply TLS certificates. So any SDK that you're using, or if you're using it on Android or whatever, you can simply plug these certificates in and they'll work. They're just like any other TLS certificates. Does that answer your question?
Somehow, we just use that network line for VPN connection. So there must be some option to input the certificates. I have not checked it, but the Juniper people here may be coming from that. Is there an option to include the certificates, your certificates into the network for VPN?
Oh, so you're using the certificates for a VPN?
Yes.
Yes, so if your VPN software or hardware, whatever you're using, allows you to upload the certificates to be served up to establish the VPN connections, these certificates will work for that. The only caveat is that your VPN device will not be able to auto-provision the certificates when they expire. Most certificates expire for a year or two, so you're not in your device that often provisioning your certificates. So they'll work in your VPN, no problem, just like any other TLS certificate, but you will need to re-provision them every 3 months.
Thank you.
Yeah. Rick, you're back.
Yeah, sorry, I'll keep this short. I can see it's good. And again, this is just about more the certificate question. So your identity here is proven by Let's Encrypt through the DNS. The fact that you have the DNS record for your website is how they determine that you are who you say you are and how the certificate is generated.
So technically speaking, what happens is because you have the public DNS entry,
Yes.
the Let's Encrypt client can go to the Let's Encrypt API, get a unique token, expose that on a public URL, send the request back to have it verified. Let's Encrypt comes through the front door, verifies that unique token is there, and then continues on the process verifying to the owner.
Okay, good. Thank you.
Yeah. Any other questions? All right, this is all stuff here, and it'll be on the SANOG side, I believe. So thank you very much.
Thank you, Ashley, the techno geek. So it was a really good presentation. I have a small query for everyone. I think there are so many ISPs here. So in Nepal, like for an ISP, in a 1 month, how many times you got a DDoS attack? Anybody from Nepal ISPs? No DDoS attack? How many times? If there is no DDoS attack, then we will not see the next slide. How many times? Yeah, Samit. And what is, if you can say the volume also?
Probably every day.
Every day. So how much the volume?
Volume are very small. So
Okay.
for us to take any action.
So because I was just watching my network element. So yesterday night I got a DDoS attack at my Gozel clinic. So that is why. Thank you, Samit. So that is why. So the next presentation is very much interesting and important because we can understand that how we can mitigate the DDoS attack through a community tool. So may I join your hands together for Mr. Fakrul? He is working now in Ethnic, and he was my friend in Bidinok and my colleague also in Bidinok. So welcome you, Mr. Fakrul.
Good morning, everyone. So, thanks, Anmol. It's good to be back here in Kathmandu after, I think, SANOG12. So, yeah. So, my name is Fakrul. I work for Ethnic as Senior Training Officer. So, mostly I do training and other stuff. But this talk is primarily the experience I had handling DDoS and other related stuff in my infrastructure. And I'll try to put all those things in pieces with configuration. So give you an idea what are the freely available community-based tools which we can try to incorporate in our infrastructure and try to deal with those DDoS. As Simon says that in the introduction, how many DDoS you are facing every day. It's not how many, I think it's going on continuously. Is the issue where you notice that you are under DDoS or not, right? Unless your customer is complaining that some site is going down and you're there, it's not accessible. So by definition, DDoS is or the DDoS distributed denial of service is the agenda they have is to perform an attack which will deny your legitimate user not to access the web services or the other services you are providing to your customers. So it may be on your DNS infrastructure, it may be on your web server, or maybe your link connectivity or your router also. So the basic idea is to deny the actual user not to have access to the services you are providing to your customer. And it comes with many forms and with many vectors. So it can have layer 3 DDoS attack, layer 4 goes up to layer 7, which is very slow and low. It's hard to detect until unless you have a proper monitoring tools in place and identify whether the service is running or not. And last couple of years we saw a radical change. The motivation under the DDoS is previously the idea is the DDoS infrastructure. They choke down your bandwidth, and none of the customer can access to your infrastructure. But what we saw for a couple of years is that the bad guys use DDoS to cover up other security incidents. So maybe they hack your server, they have your data leakage, then they do a DDoS on your infrastructure. The fact is, when you have the DDoS, there are a lot of traffic going on in out, logs are saturated, so your people are dealing with all those issues, and they forget that something goes wrong in the background. So the ideal target for the bad guys is to steal all those data, they run a DDoS so that they misguide you and they send you some other track, so that they can cover up them up, right? So and as I said, it comes with different types. So roughly we see two types. One is a volume-based attack, and one is application-based. So volume is like choke down infrastructure. Couple of years back, when Cloudflare helped Spamhaus with their DDoS mitigation with roughly 320 Gbps of traffic. It's back 2 years back, I think, 2 or 3 years back. Last month, BBC noticed that they have under a huge DDoS attack. Community saying there is more than 600 Gbps. So if you remember yesterday's presentation from Nepal, I think they have how many? 60 Gbps of traffic. So you see, it is possible to take down a whole nation, the amount of bandwidth they can generate. And what you need a few good ISPs who can allow you to spoof the IPs, and you have a good open resolver community. They will give you a free open resolver. You just do an amplification, and it's quite pretty easy to launch this amount of traffic and pump to any of the infrastructure. Along with that, we see a lot of application layer attacks. So it's mostly on HTTP, on the web services. So they are very slow. It chokes down all the Apache session you have, all the TCP socket you have. And if you look at the bandwidth, it's very minimal. But if you look at the session of your Apache web service is running or an Nginx is running, it utilizes all the session and socket you have on your web service. So to address those issues, there are three phases is very important. One is preparation, detection, and mitigation. I saw people when they are under DDoS attack, they try to Google out and find what available solution they have, and believe me, it doesn't work, right? So you need to have your understanding on your infrastructure, what you have, what are the security threats, what might have, and what are the available solutions you can have. It depends on how much money or the investment or how much management buy need. There are a lot of tools out there, but mostly I talk from the next slide is those are free for the community. You don't have to pay anything for those services. And security, DDoS is like the other security solution. It should be a layered approach. It's not like a Matrix movie, blue and red kill. You take the blue kill yourself. It's not like that, right? So you need to find out really careful and put all those pieces in place before. And this is the preparation phase, which should be in your PCP and at least. When you have all those in place, you prepare and you know what you need to be done when you are under attack. And the next important thing is to detect as quickly as you can detect that you're under DDoS and what are the source, what are the destination, and what kind of attack this is. Then it's very easy for you to go to the next phase, to the mitigation phase. Mostly what we do with the mitigation is that it's kind of scrubbing. We send all the traffic to a scrubber. They clean all the stuff, they do the magic stuff and send that good packet to your infrastructure. So these are the three phases. It's very important when you're dealing with the DDoS. So the tools we work on is these three provided by Team Kimru. So one is the Bogon filter, one is the flow sonar, and UTRS. We call it unwanted traffic removal service. So I'll go all those three with a configuration example and how it looks like and how it helps me. So I think the first one you already know what is Bogon, right? So all these prefixes, the bad one, which should not be in the internet infrastructure. So RFC 1918, 5735, or other prefixes which are not allocated by IAM. So those are the Bogon. So, and the statistics shows that those Bogon prefixes are used and spoofed launch a large amount of DDoS attacks. So it says if you can filter Bogon, it helps you to at least mitigate 60% of the bad or the not traffic you have on your infrastructure. So how can you filter those out? It is very easy. If it is 1918, I know what are the prefixes. I can make a static SCL, put it in my router in, and deny all those packets, right? But keeping up with all those allocated, non-allocated IP addresses is very hard. So you need to go and check what RIA is doing, or which IP calls to the prefixes, IANA allocated to some of the RIA. So it's very tedious, and you need a full dedicated team or person who will go and deal with this stuff. So what Kimbru does is they provide you a BGP feed of those Bogon filter, so you can do a eBGP multi-coming with Team Kimbru, and they will feed all those Bogon lists, and then you can drop those or null those out, whatever you want. You have, if you are more curious, you can forward those in any of your malware analysis tools and to see what are the traffic coming on from which sources to these Bogon prefixes. Right. So the idea is not a static list. So this is an example of, I know it's very small from the back, but I will share those slides in SANOG website. So what it does is, those are all BGP configurations. So you did the BGP membership with Kimbru, and they always need a password, identifier authentication with the neighbor session. And what it does is that you tag it in as a community, tag and match those, and you can forward those to any of your private IP, or you can put it in another. So IP of 1.0.21 null, or you can forward it to any of your internal servers, so that you can capture all those traffic. If you have a skill set, you can analyze those traffic to see if anything goes wrong with that. So it's very easy. So it's the same with the V6, so you can have two sessions for V4 and V6. And the output looks like this. So if I see an output of 31.22.8.0/21, so I'm receiving it from AS65332, the US number of the team they will use a private address for the peering, and the community is 65322.17821. I match with the community, then no export. Then if you have a community, then rest of the BGP stuff, right? So you do whatever you want all those community. You can put those in null or forward to someone else. This one is today's statistics. So far, I'm receiving 3,714 IPv4 Bogon prefixes and 65,788 IPv6 Bogon routes. So if you see the IPv6 routing table, I think the way I see it from my router is only mostly 30,000 prefixes. 29,000. So if you see the Bogon, we have much more Bogon than the actual IPv6 prefixes we have in internet, right? So that helped a lot with those filtering. How we get those? So you send a mail to bogonrs@kimbru.com. They will check, and you need to tell whether you need a full Bogon list for IPv4 and IPv6 or both. What is your AS number and which IP address you like to have as a peering IP. They need an IP MD5 authentication, and they prefer to have a PGP public key to do a secure email correspondence with you while troubleshooting all those things. So as a reference link here, you can go to the Team Kimbru site and apply for this one. So that's the first tool they have for the community, the Bogon filter. The next one we have, we call it Flow Sonar. So you filter out the Bogon, and if you remember all those three steps for the DDoS mitigation, detection is very important, right? So Flow Sonar is basically, if you have experience working with the NFSAN and NFDump, it's basically the same switch framework platform with a special built-in plugin developed by the Kimbru team. They call it DDoS Running. So with this plugin, they will basically show you what the IP address is in your infrastructure is having issues. So who hosting malware, who has open resolve malware, proxy, and all the stuff you can see from the screenshot. So they will tell you what are the compromised machines and what are the CNC hosts in your infrastructure. So if you see the screenshot here, it's like NFSN and NFDAM with a special plugin. You see on the bottom right corner, it tells what the time, the source IP, destination IP, what port protocol, and what kind of session they're trying to open. So it gives you a very good, clear understanding on your infrastructure. So now you can proactively monitor those things and tell your customer that, okay, or your downstream that, okay, hey, your IP, this IP is doing something bad in the infrastructure. Can you see and do? It helps a lot when you are under DDoS also. So you can use NFSN and NFDAM with a specific time frame and see what are the sessions are opened, in which destination, and you can easily find it out. And the beauty with that is that team can basically send you the hardware. So if you apply for it, if they allow you to host a flow runner, they'll send you a server and a router. So it's a free hardware. So the important thing is you need to have a good understanding with your customs, clearing all the stuff, because I had bad issues with clearing all those routers and servers when they send from team. So it's really painful. So I didn't know how to deal with this. But the beauty is that they will send you the hardware, you set those up, and you'll have a full-fledged NFSN and NFDAM with all those plugins in place, right? So, and the next one, the third tools they provide is pretty new. It's been a 1 year they're providing these services. We call it UTRS, Unwanted Traffic Removal Services. So the basic principle is that they use remote trigger backhauling. So if I quickly go through what is remote trigger backhauling is that you have an IP address of a block 2030.1130/24 and 113.114 you are using in your web server. So it's pretty easy. For your connectivity with upstream, you announce /24 to your upstream and your server is up and running. And recommended is to have TLS everywhere, right? As the STL says. So everything is very good, well and running, but the next bad thing happens when you have a DDoS attack. So what happens is that someone launch a DDoS attack from external side. It will saturate all the links you have from your transit provider to your service. So it comes to the transit provider to the P router of the service provider, then the C, and it will have a impact on your web server. So it's been a volumetric attack on the infrastructure. So what we do with the remote trigger backhaul, or the manual process we do is we call up our upstream, say, hi, I'm under DDoS attack from my IP address is, can you please put a null route for that? So what they do is they put a manual null route in any of the core router. It depends how their infrastructure is running. And for all those traffic, it will be dropped from the infrastructure. But think about if the DDoS attack happened on like 2 in the morning, 4 in the morning. Do your upstream provider has enough resources who have access to the infrastructure will do this for you, or you have to wait till 9 in the morning and the people come and they'll drop an hour for you. So the process we do is we do use a community tech. So you need to have an understanding with upstream what community they allow you to put. So you do a BGP community with them, you announce them with a specific community tag what the upstream allow you to do. And if you tag that and announce it to your upstream provider, they'll automatically put it in an route. So it's pretty easy. If you want to withdraw this prefix, you just remove this from your infrastructure and your upstream will automatically remove that. So that's the basic principle of the remote trigger backhauling we do, and that's what we talk about TCP. So and yeah, so when you have those announced, you see it will drop from the transit one or the transit two from the core of the upstream provider. So as I said, the UTRS TeamQ is providing is based on the same basic principle. So they allow you to have a eBGP multi-organization with them, and you tag those prefixes which you think is under attack, and you announce those things to TeamQ or TBS server. And you can only announce a /32 at a time. So yeah, so what you need is that your infrastructure should support and you know how to tag those in community and announce it to the TeamQ server. I think they are running XLBGP in the core. They take all those prefixes, and all the other participants in the UTRS basically receive those prefixes and they drop those from the infrastructure. So if you think it's very, very wide when all this community grows and you have a lot of people connecting with the UTLS, you drop it from your infrastructure, they'll basically drop it from their iPod, right? So it's save a lot of bandwidth from your upstream also. Configuration is straightforward. So you build session with them, you match your prefixes in an SQL with a community, and you announce those through a BGP session, right? And what you do is you only take /32 prefix from Kimbo also. So if any other members is dropping any of the prefixes, you drop it from your infrastructure also. So there's a check and balance. You only can now out the prefix you want, not other prefixes, right? So how you can apply for this one? You can go to Kimbo site and with this URL, you submit a form there, you submit with all the details, emails and other information. And they'll do a quick check with the who is with RDB or other IR database to see whether you are the legitimate user of those prefixes or not. And they're very cautious of those things. So they take a time with all those validation and verification. And when you are done, you can set up all those configuration in infrastructure. And that's very good FAQ list. If you have further question on how they're doing it, why they're doing it, what are the other benefits they're looking at, what are the other value addition they can do with the flow spec and other thing. There are all those descriptions there. So to open up the audience, I have a question to you. So how this utilities is varies from other remote trigger backbone we are doing with the upstream. So I'm not answering this question. I'm here till the end of this conference and the workshop. So feel free, and you think this is a thought process for you that how it varies from other traditional activities you are doing with upstream. So let's have a thought with that. There are a few other efforts going on. It's not only thinking. There's a big of in SANOG meaning this. They call it DOS attack. So it's kind of a list of what to do or not to do. So that the preparation you need to be there before you selecting a DDoS tools. What you need to be done when you are under DDoS attack. After DDoS setup, the minimum tools and techniques you need to be in place. ISOC has a very fancy name, come up with a routing resilience manifesto. They call it mutually agreed norms for routing security. So if you go to this link, it's kind of the same stuff. They talk about the PCB38, source filter, and other good stuff we talk in all the time. So it's kind of a mutual understanding and agreement to say that, okay, if we apply for the routing resiliency manifesto, it says that okay, you are minimum doing all those things in infrastructure, and they will list you on their site. So your customer can go and see, okay, your logo is there, your company name is there. That means you have some effort to run a very good, clean infrastructure by you, right? So these are the other. There might be some other. If you know, I'm glad to know all those community efforts that we can place to fight all those diseases. So before finishing my slides, I will ask you to another tools and technique, which is very important to fight against the DDoS issues. Keep coming just in DDoS. So I saw people get panicked when it's under DDoS, especially in this region, because we are the same guy handling customer services. My customer is calling, my web server is not running. I'm also responsible for managing all those infrastructure. Right? So it's very hard to get concentrated when you are under DDoS setup. So segregation of duty, I think, very important in your BCP. When you are under DDoS, who will do what specific task, what the key resources, and it's very important to identify all those as early as possible. Right. So that's all from my side. So if you have any question, I would like to take this now.
Hi, thanks. Actually, goes with PCH. You announced a /32 and upstream is automatically dropped. The customer then is effectively knocked offline. Is there a follow-up DNS change or WEP that allows the customer to come back online? Because presumably the attack will still persist, just the traffic's not allowed through.
Yeah, so if I understood the question correctly, if you like drop this /32, your traffic dropped and the service is not running, right? So yeah, so there are no straightforward answer on this, because if you change the DNS, then those attacker will basically again come with the /32. but there are some discussion with segregate. I mean, it's called a community job, but for a specific upstream. So, the idea is that you tag it as a community, but you announce it to your upstream so that it is not dropped from everywhere from a specific target. But it is quite tedious, as you said. It's right. If you change the DNL, that will be also there. Yeah.
So you basically filter on source.
Yeah, source. Yeah, because you can't drop whole internet from using the RTBs, right?
Yeah. Thank you.
Any other question? Question goes 1, question goes 2, question goes 3. Thanks.
Thanks, Prabhu, for this nice presentation. Maybe, yes, we are using this free of this tool, RTPH, and also we have a flow sonar, so we are using community for black hole. So my next presenter is from Harikini Electric. His name is Anurag Bhatia. This is a very interesting topic about the disconnected network island. So please, Anurag.
Good morning, everyone. I'm Anurag from Harikini Electric. We are IP backbone and data center provider offering services in US, Europe, and American market and Asian markets. So my presentation today is about disconnected network islands. So how we have multi-geography islands. Broadly speaking, there are two possible ways to have multi-geography islands. One is to have those islands connected together with the backbone, and the second is to have completely disconnected and isolated setups with their own set of transits. So you might have a network in Asia, you might have a network in Europe, both with their own transits, but using the same ASN in each location. Here's an example where we have a network with a connected backbone. Here you can see POPs are connected over a layer 1 backbone. And here's a generic example where you might have a network using the same AS numbers, but completely disconnected, completely isolated, and traffic flowing between those backbones over regular internet transit. So this talk is primarily around this kind of setup where you have disconnected islands and you start announcing routes from those disconnected islands. So a quick idea about what are the disconnected islands. Primarily, these are the networks where you are operating under the same ASN but without any logical connection. This includes any possible point-to-point link, any possible layer 2 link, any possible logical link over any terminal protocol. And one key factor around here is that routing between these networks happen over other ASNs. So you might have a case where traffic from AS1 is flowing to AS2, which is further going to AS3, and then again it is going to a destination which is AS1, which started the traffic, from where the traffic originated. So coming to disconnected island routing, what does that mean? This is a term we are using here to explain where you have multiple islands and you're announcing routes from which you are indirectly learning. So you might have a network A in, say, Asia Pacific region, you might have a network B in American region. Now you start learning routes by disabling the BGP loop detection, and then you start leaking those routes to the upstream providers. I'll get more on the loop detection in upcoming slides. So specifically, this is a scenario which is not possible automatically because BGP takes care of that. the loop detection always ensures that the same ASN is the AS which is originating a route denies all possible routes which have the same ASN in the AS path. And of course, the leaks happens when you have just a prefix-based filter, which I found this is quite common. A lot of people just filter out the routes based on prefixes. They don't filter routes based on the AS path. So there is a high tendency of leaking routes which you are learning indirectly if filters are not set right. So coming on to the BGP loop detection, there we go. So as I said, this is one of the fundamental features of BGP. It ensures that if you have the same ASN which is originating a route, it denies that ASN from the path. This is enabled by default. One can disable it, so you can allow AS in case of Cisco, and you will start hearing your own routes. So let's say you are running AS1 and it is connected to AS2, then AS3, 4, and this is the path. You might, if you allow AS in, you will start hearing the routes originated from AS1 in a separate disconnected island. So what is the impact of disconnected islands here? So I'll come to the impact first before I share what we found in context of. So I'll come on the impact first before we get to the results. One of the serious impact out here is that it shows very crazy relationships. So you might see on tools like bgp.he.net or RIPE-stats that a downstream suddenly starts appearing as upstream for someone else. You might see a very small network appearing as an upstream provider for a larger network. And this, of course, has a very serious impact in terms of bandwidth. So, for example, if you have multiple networks and you start receiving routes of your own network in different locations and start leaking, there's a high possibility that you will be wasting a lot of bandwidth. So, if you are announcing certain routes in Asia Pacific region to transit provider, and you start learning your routes in the American region, and you start leaking those routes to the upstream provider, there would be a high tendency that traffic might flow from that direction, causing a lot of wastage of bandwidth to your American transits or the other location transits. It will be literally coming to the POP and then leaving the POP, going back to the other location. So literally 2x bandwidth wastage. It can cause trouble in terms of filtering. This is slightly unique thing here. I'll come more on this when I share the results on how it can cause problems during filtering. In our study and data, we found that a lot of these cases are visible because of bad setup and bad prepending that can cause it. And so there is a high tendency that someone might just filter your route, which you don't expect to do. And of course, it causes noise in the routing table. So Philip gave a nice presentation yesterday on the routing table. I'm sure these are some of the things which appear in those reports, directly or indirectly in terms of noise the report shows. So the study we did about such islands was pretty straightforward. It was based on the logic that if we see the routes in the routing table where an ASN is repeating, and this does excludes the case of AS path prepending. So you can have AS1, AS2, AS3, and then AS1 again, and then some other ASN. These are all some special cases because by default these are denied by the behavior of BGP. So whenever an ASN is repeating in the AS path, it is usually an interesting case. It is usually something to explore more. So the data is based on RIPE, RIS terms, which we pulled from 2010 till 2015. We did this study in September, so data is pretty much based on till September 2015. So here's what we found in terms of results. Broadly speaking, there were 4 categories in which this kind of behavior was showing up. One was, of course, that a lot of people mistype ASNs while doing prepends. So a lot of vendor configurations say that to repeat ASN just to prepend an ASN just do AS2, 3, 4, and people tend to copy them, and this results in AS1, 2, or 3 appearing in the routing table quite often. The other thing is the real disconnected network island case, which we did found in certain instances where literally someone is running their own routes and then leaking it to someone else. I'll come on the example as part in upcoming slides. And there can be a case, so in the fourth one, specifically in IPv6, we noticed that there are cases where people are using their own ASN in mixed fashion. So it's like you have AS1 and AS2, and then you start using them in a mixed manner. You use AS1 connected to 2, and then again 1, and then again 2. So such things do happen, and they also give a pretty interesting idea about such setups. And of course, possibly some other miscellaneous behavior. Since we found quite a lot of ASN showing this behavior, it's not, it wasn't really possible to contact each of those network operators and figure out why exactly those routes were appearing. A lot of this data was historical, so there could be something which came up in 2010, which we are presenting now in 16. So it was really hard to actually comment on why certain routes were in certain way. So in our study, we found there were around 227 routes, and they appeared, within this time frame of 5 years. And these are all the routes where they appeared multiple times within the same AS path. All these belong pretty much to all RIRs. We did map them to countries using Dean Cameron's ASN data, and in terms of RIR, they were pretty much spread across all RIRs. There wasn't any specific trend. The only noticeable trend was wherever network operators are more, this trend is slightly more. So possibility of miscommunication is higher in case of regions with higher internet penetration. And in terms of unique routes, we saw somewhere around 27,000 unique routes with 3,000 plus unique prefixes with such behavior. So here's an example of mistyped ASN. This is not a real disconnected island example. This is clearly mistyped ASN case. So if you notice, here AS55470 is originating prefixes, and they seem to be prepending quite a few times, and possibly while prepending, they added an extra 5 in their configuration. So in the red, you can see it's 55540, and there are a lot of routes with such behavior. So you will find often that the ASN which appears in the crazy manner, it's very much related to the origin ASN. This was one of the very large cases. So this wasn't real disconnected network island, but this shows the behavior where you see the same AS repeating and being disconnected from itself, being connecting to itself with some other ASN in between. While in real, it's just the same network. It's just wrong prepending. Then some other cases where people do back prepending while using the top ASS. So here's an example. So if you look at the first line, someone prepended, this is AS132471, which prepended using AS2 multiple times. So within this AS path, there is a behavior that AS2 is disconnected to itself, as well as AS131 and 211 is disconnected to itself. And this again is very possibly an example of back prepend, because if you look at the ownership and relationship of these ASNs, you won't find much of the relation. You won't really find AS2 being a transit provider anyway. And it's a ASN belonging to an American university, while this ASN is completely from a different region, the downstream one. So such examples do come up quite often, and they are mostly with top ASNs, usually 1, 2, or 3. And here comes a case of real disconnected islands, about which this was the real interesting thing which we were trying to find in the routing table. So this is specifically a case from some of the Indian networks. You will see that AS132220 is announcing routes out to AS18101, which is quite large Indian ISP, and it is carrying forward those routes to 24029, which belongs to Nixie. And till this point, it seems quite logical and quite decent. Well, then you will all of a sudden notice the same ASN which was originating those routes. It is learning those routes again itself from the BGP session in Nixie, and then leaking it further to its upstream providers. This clearly shows that the router which is connected here to to AS33480 and Nixie, that has disabled the BGP loop prevention, and somewhat probably having outbound filters based on the prefix only. So it's not announcing the routes which it knows directly. It must be having open filters for its own prefixes from wherever it learns. So this is showing as 24029 is upstream for 18101, which really it's not. It's just an exchange ASN. There can be other instances where you will see, other than 24029, some of the other smaller networks, and they would show pretty much the similar behavior, that all of a sudden a small network appears as an upstream provider for larger networks. And this is quite visible in a lot of reports around the world, around the BGP table. And here comes a very interesting case from the IPv6 world. So AS209, which belongs to a very, very large ISP, and AS3908, that also belongs to the same ISP. It seems to be in use in some kind of mixed manner. So you will see parts where 209 is connected to its own other ASN, and then again which is connected to 209. This again is clearly a case where either loop prevention is disabled or something else is going on, which is hard to predict. But definitely a case to put in, so a case to consider. And here comes an interesting case of longest IPv6 prepend. So yesterday, Philip was showing some of the interesting prepends. 50 prepends or 100 prepends. This is a case where someone did a prepend 20 times, and while prepending it 20 times, they just wrote the ASN in wrong manner, and this again resulted in the fashion where you have your own ASN disconnected from your other side of network, which in reality is not the case, but it just appears like that. So best user practices for avoiding this kind of problem. One thing we need to understand is that disconnected island as a setup is not a problem at all. It is perfectly logical. There can be a lot of business cases where, let's say, access network is getting into a market and deploying network without connecting to the other side of the network. So you might have a network in say a country like India. You might have network in Delhi. You might have network in Mumbai with its own set of transits. It's just perfectly normal, and you can use the same ASN. What is bad is to learn your own route and then leak it further to the upstream providers. That is something which one should avoid. So possible best user practices for avoiding this kind of situation. If you are running completely disconnected islands, and if you have the default route, possibly you can keep the BGP loop prevention enabled. You should not explicitly disable it and let the default route to take care of traffic flow. In case you have a specific topology where you don't want to have default route, there can be certain real cases where you want to skip the default route. And in those specific scenarios, you can disable the loop prevention, but in those cases, you must ensure that you explicitly filter routes which you are announcing to the upstream. You should not announce the route which you are learning indirectly from your other side of the network. So that's pretty much it. Any questions?
Are there any good tool sets out there that you can advise people running their networks or wanting to monitor their own BGP feeds for this sort of problem? Or is this all just going through and scripting and keeping things manual?
I'm not available of any open source tool which can do it as an open source package as a whole. Of course, the routing dumps are available, so one can skip around it and look at all route dumps from Oregon or RIS. In terms of tool, I think most of them are pretty much commercial in nature, which do alert people of that their ASN appears in certain phishing manner.
I have a question.
Can you go back to the slides? Where you show 9498?
This is the one?
Yeah.
Yeah. On the fourth line.
Yeah, one line. So still this route is available?
Yeah, I guess this is still available. This specific slide has, so a lot of data here is historical, and you might not find those routes anymore in the routing table. You will, of course, find them in the routing terms. But when I checked last time, this setup was pretty much visible. Thank you. And here this specific, it's interesting that this specific case 1322220 is showing this behavior even with other transit providers as well. Like, it's not just limited to 18101, it's also with 9498 and 55410, which are pretty large providers out in that region. Any other questions? Great, thank you.
Thank you, Anurag. This is our last presentation. We are almost getting our time. So this presentation will be on MPLS traffic engineering, and it is from Juniper. I think you can introduce yourself. And he is from Bangalore. Bangalore. Thank you.
Hello everyone, I am Chandra from Juniper Networks. I have been working in Juniper routing protocols development team for the past 7 years. I am based in Bangalore. Today, I will talk about some of the recent enhancements that has been made in MPLS traffic engineering for MPLS traffic engineering. The recent enhancements has been made specifically to address some of the operational challenges that we have observed over the years in deployments of RCPT. So I'll very quickly recap some of the motivations for why people use MPLS-T, and then go into the operational challenges and the solutions. Each of the operational challenge and the solution deserves a separate topic, per talk, that 25-30 minute talk by itself, but so I'll very quickly go through a brief outline of each of them. A quick recap of the motivations. I have listed out 4. So, bandwidth reservation, fast readout, prioritizing traffic, and class-based forward. So, one point I want to highlight here is that in the case of bandwidth reservations, what we have seen over the years is that from the motivation being just to provide some kind of a quality of service for some certain classes of traffic. So we have seen the motivation for bandwidth reservation has been to increase the utilization of the network. So to give an example, so some of the operators who have deployed MPLS-T have been able to increase the utilization of the networks up to 80-90%. And another point I want to highlight is in the case of
prioritizing traffic. What we have been seeing recently is that this is primarily used in the cases where you have a fat aggregate bundles, and since aggregate some say multiple 1 gig or 10 gig links, and most of the failures that happen, which is the link failures that happen in the network, don't necessarily translate into L3 interface flaps or any IGP topology changes. But what happens is that the bandwidth on the link degrades, and during that time, the operators would want priorities when which traffic, which of the LSPs, which of the classes have to be rerouted, which of them should not. So I'll go through one after the other. There are four. I'll go through one after the other. The operation challenge and the solution. So this is in practice what we have seen is like so operators start at a particular LSP scale. Let's say we have 2,000 LSPs initially. That is on one. There is a maximum LSPs that is present on one router. Let's say they start at 2,000, and soon what they find is like within the number of LSPs that a router has to carry either doubles or trebles, or sometimes it goes up some 5 to 10 times within a few years. And what that brings up is this operational challenge, which is the implementation that actually works well at say the initial scale don't necessarily do so and gives operational challenge when the scale increases. So the first challenge is the LSP provisioning. So we have put load balancing also because like when operator wants to deploy RSVPT, so what they do is like they do LSPs, provision the LSPs, and traditionally the method of reducing operational overhead for LSP provisioning has been to some twofold. One is implementations supported creation of LSPs automatically whenever there is a BGP, new BGP next hop is discovered, or some kind of advertisement in IGP saying this is part of an auto mesh group, and so the LSP gets created automatically. But as I highlighted in the motivation, so one of the recent trend has been the motivation for bandwidth reservation has been to increase the network utilization, and in such cases, it is somewhat impractical to constantly provision and deprovision LSPs in the network. So what we have seen is like the auto bandwidth feature functionality, which is in fact available in multiple vendors implementations. So auto bandwidth is a functionality in which the operator configures an initial bandwidth, which is the bandwidth of a traffic unit path, and the operator doesn't want the bandwidth to decrease below that. And if the traffic on the LSP increases beyond a certain, again, some of the configured parameters, the ingress head end will resize the LSP automatically, which means it will re-signal the LSP at a higher bandwidth in a make before break fashion. So what we have seen is this is something that so the operators who deployed RSVPT for increasing utilization have increasingly fully moved to using this auto bandwidth feature. It does help to reduce the operational overhead, and it is somewhat a very successful feature. And again, as I said, it's probably available in multiple vendor implementations. If auto bandwidth is actually quite successful, then there is still some problem, which is the problem of say load balancing, and there is some other problem which I would try to explain in this slide. So consider this network in which we have head end, which is R1, and there are some LSPs in the network which I have not yet shown. Assume that on those particular 3 links going out of R1, all of them are 100 meg, which means the bandwidth available from R1 for any new LSP is not more than 100 meg. That is on one of the link, on each link. Now, assume we have, for some reason, this is again a very simplified example. So, assume there has to be a LSP from R1 to R5, which was probably previously down, and now it comes up. I should have a bandwidth of 300 meg. But all the possible paths from R1, which is all the 3 links that is emerging out of R1, each of them are 100 meg. So the LSP actually cannot come up. And so the users of auto bandwidth have begun to face this problem as they attempt to increase the utilization of the network beyond a certain point. And so what usually was done is like they try to intervene through some scripts, automatically try to provision some LSPs, additional LSPs. Say it's like instead if it's 300, try to put 100 3 times, and so operator now has to intervene. It's like it's something that the head end does not take care by itself. So what is the solution? So what operator does as solution is to, instead of provisioning say LSPs, what the operator has to provision now is a container LSP. So it's as the name indicates, it's not a real instance of an LSP. It's just a container, which is the operator has to say from R1 to R5. You have a container LSP, and these are some of the basic say parameters. I have not listed out the details because, as I said, it's going through the dates would actually extend the time. So operator provisions a container LSP, and now we have the same problem, which is what we saw in the previous slide. We have 3 links which have just 100 meg available bandwidth, and we need a LSP of 300 meg. So in this case, because it's operator has install the provision a container LSP, the head end node will first try to do a CSPF path computation, find that it cannot detect a path for the LSP. And because this is a container, now it does something different, which is like it tries to find out if I can find multiple LSPs, say first 2. It tries to actually determine what's the can I fit in this request. If I can't fit in with just one LSP, can I fit in with multiple LSPs? So again, it's like it's the way the fine tuning of how this can be done by user configuration, which that I'm not actually dealing with now. But what will happen is, like, because this is a very simplified case, so the head end will find 3 LSPs, 3 paths, and it will automatically provision 3 LSPs. In fact, in terms of the nature of these LSPs, they are not any different from, say, the LSP that the operator manually provisions. That means that the other routers in the network, that is apart from say R1, say R2, R8, A, B. These router, there is no additional protocol extension here. So which means like you don't have to, the operator doesn't have to upgrade any transit routers. You just have to upgrade the head-end routers, and the head-end routers will automatically create those LSPs. So each of them is a member LSP, and so what R1 does is like it does load balancing. As this is not different from user provision individual LSPs. The whatever load balancing of functionality that is already available on implementations, that will just automatically work. No additional things required. And if in case, if the bandwidth requirement of that LSP reduces, say, now 200 meg, and by the way, the head end will be in the case of auto bandwidth. So what head end does is like when user does tries to using CLI get the statistics of LSP, this traffic, what's the traffic rate going on the LSP. What R1 does is it automatically does kind of a stats pull from the hardware and find out, okay, so that's how it determines what's the traffic that's going on the LSP. So if R1 finds that the LSP traffic has gone down, and it's not like R1 would just simply go haywire and then simply resize or try to do all these things. It's like, so whatever the way how aggressive the head end should, that's determined by some of the fine-tuned parameters. So now we can actually merge the number of LSPs into two. So that's the LSP provisioning angle. The other is, second one is the fast reroute. Let me briefly go through the problem on the fast reroute. So here is in the same network, we have, say, traffic coming to R1. Let's say we have a LSP that's a red LSP instance, that is to R5. Assume there is a failure on along the path of the LSP. So the red LSP gets locally repaired. This is the standard FRR. And apart from, also R1 will try to now re-signal a new LSP instance in a make-or-break fashion. Once the signaling is complete, R1 will switch the traffic to the green LSP instance. So what's the problem here? So while this will work well at, say, as I said, at some scale, if the scale of the transit router is increases, so what we may find is like, in this case, R6, which is like on the green LSP path, its data plane may not be ready, and before so what R1 may do is like it prematurely switch the traffic to green LSP instance, even when data plane is ready or it's not ready on the. So in a way, it basically breaks the purpose of fast reroute, which is like minimal traffic loss. So the implementations do support some kind of a delay timer, so which is like you operator configures what time the ingress should wait before switching to the new green LSP. The problem is the time also is scale dependent. So some 20 seconds that may work at one scale may not work at a higher scale. One could use LSP ping, but the problem is like at scale again, the LSP ping needs software intervention at the egress LAR. So what's the solution? In the same diagram, instead of step 4, where R1 immediately switches, what we do is like we send a IP packet, not an LSB ping packet, it's a self-ping IP packet. The packet is destined to itself, just like the destination address on the IP packet is R1 itself. That is, R1 sends a packet, IP packet to itself with the source address as R5. But instead of sending it over IP routed, it pushes it over the LSP, which means the traffic, the packet is going over the LSP. As long as the green LSP instance is not fully programmed, data plane of all the routers, the packet doesn't reach R5. So the packet gets dropped. When the data plane is ready, R5 receives the traffic and the egress area receives the IP packet, which is IP self-ping packet. Now it sees because of PHP, R5 will directly see the IP packet, see that the destination address is R1, and the egress area hardware now powers the packet back to the ingress. Now once the R1 gets the packet back, it can switch to the green LSP instance. So here the advantage is like we don't need any operationally challenging knobs that has to take into account the scale, or we don't have to worry about R6, the egress area being overloaded with LSB packets. So the third challenge is monitoring LSPs. So usually monitoring is done either through some form of say SNMP gets and mostly some kind of pull mechanism from any external agent, external station. So the better solution is to do some kind of push-based approach, where if it is possible for a kind of a template to be given, such that, say, for example, when we want to say there is a template in which both the transmitter, which is on the router, and the collector, which may be on the router, which may be outside. So they have a template in which the template is defined, and then the transmission and the processing code gets automatically generated, both at the transmitter and the collector. So once the template is set, it is now it's now pretty simple to just I've just given just a slight example where you have what you call a sensor, which is there are some properties for the sensor. It says like so the example given is like for LSP, there are two sets, like events and properties. So what's the property of the LSP and what are the events happening for the LSP? Like LSP is going up, LSP is going down, it has been locally repaired, etc. And there are also additional parameters like what is the telemetry events have to be sent. So once we do that, the additional overhead of trying to monitor is actually now reduces. So it's now like once the template is defined, we can now do the LSP monitoring at scale. The last one is the protocol traffic overload. So historically the MPLS traffic is done through as it has been done through RCBT. Historically, the base RCB protocol is a soft state protocol and relies on periodic refresh. The default refresh interval is 30 seconds. That means like every router, if it has 10,000 LSP states, will be constantly sending out refresh messages to refresh the state. They're saying that I have a state, I have a state. And they actually use this fast rate, this frequent refresh to actually recover from any lost packets. But there is actually already a solution that is in fact quite old, which is defined in RC2961, which is refresh overhead reductions extensions, and where it's defined the mechanisms to ask for acknowledgements. So packets can be acknowledged. So the routers don't have to rely on periodic refreshes. But so which means now the default refresh interval can be now set to some non-interval value. But what we have seen is mostly the operators, mostly the max they get to mostly is like something like 2 minutes. So it amounts to something like but even that's actually very rare. Most of them set it to 1 minute or less than a minute. And why is that? The reason is that the implementations did not support the 2961 properly. What 2961 defined was mandated asking for acknowledgements, that is reliable delivery, only for the state messages, which is path, recipe, and all that, but not for the tier down messages. So which means if a router is deleting its state and it sends a tear down message to its neighboring router, and if for some reason that message is lost, now that if we have a long refresh timeout, so the other router will be retaining that state for say 1 hour or multiples of hours, depending on the refresh interval set by the operator. So the once the if implementations implement 2961 fully, which is for path tiers as well as error messages, then the operators can now set the refresh interval to a long interval, and that will help reduce in fact, completely solve the problem of additional protocol traffic load in the network. And another problem was that there was no flow control because RCP was directly running on top of IP and it's not running over TCP. But again, with 2961, it was possible to do some form of flow control, which is you send 100 messages, didn't get any response. So that means like there is no point in sending 100 messages immediately again. So there's some form of flow control was possible. So implementations, if they implement 2961 properly, so this problem can fully be solved. So we have seen that most of the deployment challenges that we see are in fact solvable, and the solution current status is like, in fact, these solutions are already shipping in software, and some of them, all of them are actually under trials for in customer deployments now. So these are the references. Yeah. Thanks. Any questions?
Any questions?
Thank you, and thanks to Juniper also for giving us two good presentation yesterday and today. So we are running a bit late, so we will start our closing ceremony at 12. So we are going to have a very quick tea break and then come back. Okay, thank you.